This video derives the Hertz normal contact law. The final result is the normal force equals 4/3 E star square root R star times indentation to the 3/2. We will not assume this formula. We will build it from geometry, elasticity, boundary conditions, pressure integration, and dimensional checks. The side view shows the contact diameter. The zoomed front view shows the actual circular contact patch. The unknowns are the force, the indentation, the contact radius, and the pressure field. The normal force is positive in compression. The indentation is positive when the bodies approach each other. The contact radius is the radius of the circular patch, and it grows with load. The side view contact mark is a diameter, not an elliptical area. These assumptions are the allowed operating conditions of Hertz theory. Small strain and linear elasticity allow displacement superposition. Homogeneous isotropic solids allow standard elastic constants. Smooth non-conforming surfaces justify a point-like initial contact. A small contact patch and small slopes justify the half-space approximation. Frictionless contact removes tangential traction. No adhesion prevents tensile contact pressure. Now the assumptions become boundary conditions. No adhesion means contact pressure is non-negative and zero outside the contact patch. Frictionless contact means the tangential surface traction is zero. The local geometry is just the equation of a circle. Put the first contact point at the origin and the center of the sphere at height Ri. The cross-section satisfies r squared plus zeta I minus Ri squared equals Ri squared. Solving gives plus and minus square root branches. At r equals 0, the surface must pass through the tangent point. So zeta I of 0 must be 0. The plus branch gives 2 Ri. So it is wrong. The minus branch gives 0. Therefore the exact local sag is Ri minus the square root of Ri squared minus r squared. This is geometry only, not elasticity yet. Because the contact radius is much smaller than the sphere radius, r over Ri is small. Rewrite the exact sag and use the Taylor expansion of square root of 1 minus x. Keeping the leading term gives zeta I approximately r squared over 2 Ri. The exact circular arc and the parabola nearly coincide close to the contact point. For two convex spheres, the underformed gap is the sum of the two local sags. This means the curvatures add. We define r star so that 1 over r star equals 1 over r1 plus 1 over r2. For a sphere on a rigid plane, r star is the sphere radius. For two identical spheres, r star is half the particle radius. Both bodies deform. Under linear elasticity, the normal displacements caused by the same pressure distribution add. That is why elastic compliances add and the formula is written for 1 over E star. E star is the effective Hertz modulus, with units of pressure. The Boussinesq solution is the Green's function for an elastic half-space. A tiny pressure element creates a displacement that spreads outward. For a full contact pressure field, we add the displacement produced by every small pressure element. The integral looks difficult, but the physical meaning is simple. Pressure creates displacement, and linearity lets us sum the effects. Inside the contact, the elastic displacement plus the original geometric gap must equal the indentation. Outside the contact, there is no pressure. For a smooth non-adhesive contact, the pressure vanishes at the contact edge. The radius a is an unknown free boundary. The pressure should be largest at the center, decrease smoothly outward, vanish at the edge, and remain non-negative because there is no adhesion. The final shape is semi-elliptic. This scene only gives physical expectation. The next scenes derive the formula. The method of dimensionality reduction gives a clean route for axisymmetric contacts. The parabolic profile maps to a one-dimensional profile g of x. Substituting f prime equals r over r star. The integral evaluates to x. So g of x equals x squared over r star. The one-dimensional spring displacement is indentation minus the transformed profile. At the contact edge, that spring displacement is 0. This gives delta equals a squared over r star. This is not merely undeformed geometry. It is an elastic compatibility relation. The line force density equals E star times the one-dimensional displacement. Since the displacement is parabolic, Qz is proportional to a squared minus x squared. Differentiate it. The Abel relation converts this derivative into the contact pressure. Substitution gives a single elementary integral. Its value is the square root of a squared minus r squared. Therefore the pressure is semi-elliptic. The maximum pressure is 2E star over pi r star. And the normalized pressure is square root of 1 minus r squared over a squared. The total normal force is the integral of pressure over the circular patch. A thin ring has area 2 pi r dr. Substitute the semi-elliptic pressure and use S equals 1 minus r squared over a squared. The integral evaluates to a squared over 3. Thus the force is 2 pi over 3 times the maximum pressure times a squared. The maximum pressure is 3 normal force over 2 pi a squared. It is also 3/2 of the mean pressure. The units reduce to newtons. Combine the maximum pressure from elasticity with the force from pressure integration. Substitute Pc0 into the force expression and cancel pi. The result is Fn equals 4E star over 3r star times a cubed. Solving gives the contact radius as a cube root law. The dimensional check gives cubic meters before taking the cube root. Now eliminate A. From compatibility, A is square root of r star delta. Substituting this into the force radius relation gives a cubed as r star delta to the 3/2. After simplifying, the Hertz normal contact law appears. The force is not linear in indentation. It scales as indentation to the 3/2. The exponent has a physical origin. Geometry gives a squared proportional to r star times delta. Elasticity gives pressure proportional to E star times over r star. Force is pressure times area. These three facts combine to produce the 3/2 power. The normal tangent stiffness is the derivative of the normal force with respect to normal. Indentation. Differentiating the Hertz normal force law gives 2E star square root r star delta. Since square root r star delta is the contact radius, the normal stiffness is 2E star a. The normal contact stiffens as the patch grows. The maximum pressure can be written in equivalent forms. One form uses force and contact radius. Another uses elastic modulus and contact radius. Eliminating A gives a force-only expression. The dimensional check gives pressure cubed inside the bracket and pressure after the cube root. The elastic strain energy is the work done during loading. Integrate force from zero indentation to the final indentation. Because the force varies as delta to the 3/2. The energy is 2/5 Fn delta, not 1/2 F delta. The 1/2 formula applies only to a linear spring. The surface normal stress equals minus the contact pressure in the usual tensile positive stress. Convention. Outside the patch, surface normal stress is 0. For frictionless contact, the surface shear traction is 0. Hertz stress theory shows that maximum shear is below the surface. Not exactly at the point of maximum surface pressure, because the principal stresses decay differently with depth. For two identical DEM particles, the effective radius is Rp over 2. The effective modulus is Ep over 2 times 1 minus nu p squared. Therefore the DEM Hertz force can be written as kh delta to the 3 halves, where kh equals 4/3 E star square root R star. The coefficient has units of newtons per meter to the 3 halves. Here are the common errors. Delta equals a squared over 2r star is not the Hertz indentation relation. It is the underformed geometric gap at the edge. Do not replace the 3 halves law by a linear law. For identical particles, do not use the particle modulus or radius directly. Use E star and R star. Also write contact pressure as Pc, not P. Hertz theory must be modified for large deformation. Plasticity, adhesion, roughness, conforming contact, finite thickness bodies, tangential friction, viscoelasticity, and rate-dependent collision damping. These effects are important, but they do not belong inside the clean non-adhesive elastic Hertz derivation. Every major result has a support. Sphere sag comes from circle geometry. The parabolic profile comes from Taylor expansion. R star comes from adding curvatures. E star comes from adding elastic compliances. Pressure comes from the Abel transform. Load comes from pressure integration. The Hertz law follows only after the contact radius is eliminated. These are the working formulas. The memory chain is this. The sphere is locally parabolic. Pressure creates elastic displacement. Compatibility determines the growing contact radius. And pressure integrated over the growing area gives the 3 halves force law. The classical source is Johnson's contact mechanics. Chapter 4. The detailed axisymmetric and MDR route is cross-checked with Popov, Hess, and Willett. Handbook of Contact Mechanics. Chapter 2. The scope here was frictionless, non-adhesive, homogeneous, isotropic, linear elastic normal Hertz contact.